In this video, we are going to look into conjugate beam method to calculate beam deflection. Let's use a cantilever beam as our example. Similar to moment area theorem, internal moment function is required to perform the calculation. Let's try another approach by setting the free end as our reference point. In this way, we may determine the internal moment function without needing to calculate the support reaction. After obtaining the internal moment function, we plot the bending moment diagram. Then, we divide the moment by EI, namely the product of modulus of elasticity and second moment of area. The M/EI diagram is the first step for our conjugate beam method. It is superimposed to our imaginary conjugate beam of the same length. The nature of M/EI diagram changes, and it is now treated as a distributed load that always acting away from the beam. Up next, let's determine the end condition of our conjugate beam based on the real beam. When we have a fixed end in our real beam, it should be free of restraint at the same position on our conjugate beam, and vice versa. For pin or roller support, they should remain the same. For internal hinge, it becomes internal roller for conjugate beam, and vice versa. Why do we need to do so? This is because in conjugate beam theory, the rotation of a point on real beam equals to the shear force developed at the same point on conjugate beam. The displacement, on the other hand, equals to the bending moment developed at corresponding point. For fixed end, we always assume no rotation and displacement occur. In conjugate beam case, it means this point should not contain any shear force and bending moment, and this is possible if and only if it is a free end. Same concept for the free end of real beam, where rotation and displacement exist. The best way to describe this behavior in conjugate beam is by assigning it a fixed end. At this point, we have developed our conjugate beam. It is time for the action. Shear force developed in the fixed end of conjugate beam equals to the total load applied. Since the internal moment function is quadratic, we know we are dealing with a parabolic spandrel. In this case, the total load applied equals to the area under the distributed load, which also equals to 1/3 of beam length times the peak intensity of the distributed load. Bending moment, on the other hand, can be determined by determining the product of total loading and lever arm from the fixed end to the centroid of loading. For parabolic spandrel, the centroid is 1/4 base length away from the vertical edge. Therefore, the lever arm from the centroid of loading to the fixed end is 3/4 L. We are now able to calculate the resultant bending moment at fixed end. After we are done with our calculation, let's convert the result back to our real beam. The value of rotation is negative, which means the beam is rotating in clockwise direction with respect to the original alignment of beam. The displacement is negative as well, denotes the point is displaced downward. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.